Now you can start.
Okay. Okay, let me just check that everything works.
Здравствуйте.
Okay, so my name is Mishnyakov Viktor. Good evening, everybody. I'm going to talk about my latest paper with my co-authors. About matrix models and Painleve equations, or even Q Painleve equations. So let me start with some brief motivation. In the title of my talk, there were words AGT correspondence, but I won't be talking much about AGT. In particular, I'll be mostly interested in matrix models properties, and I will discuss stuff about matrix models. So first, the plan of the talk will be some very brief introduction, which is sort of my motivation to study the particular matrix model, or rather matrix integral, which I'm going to study. It involves basically the ingredients of the so-called AGT correspondence, conformal blocks, Nekrasov functions, and the Painleve 6 equation. Then I will talk about matrix models in general. I'll briefly remind some of their properties. And then I will go into more details, talking about matrix models in MIVA variables and the precise relation with Painleve 6 equation. Next, I will describe the Q deformation of the picture and of the main properties that I'm going to be interested in. And from the Q deformed picture, I'm going to describe how to restore the undeformed situation, which I will call the continuous limit, because in the Q deformed equations will be difference. So in order to reconstruct the differential equations, we will need to take some sort of continuous limit. And in the very end, I will briefly touch upon the pure gauge limit of the whole story, and I will describe that. I will state that the properties which I will be discussing also persist in the pure gauge limit. Okay, so let me briefly talk about motivation. My motivation is so motivation comes from the AGT correspondence, which relates two-dimensional conformal blocks and instant-on partition functions of 4D supersymmetric theories. Well, at least in particular, it does relate those two objects, and these objects have various interesting properties, one of which is the celebrated formula, the celebrated statement that the Fourier transform of the conformal block at central charge equal to 1 is the Fourier transform is the tau function of the Painleve 6 equation, which goes by the name the GIL formula from the names of the authors, Gamayun, Yorgov, and Lissavi. So some references are given here. This statement was already known. Well, it was presented in detail in 2012, and since then various works have been done on this topic. This statement was proved from the point of view of conformal theory in works by Bernstein and Shechkin, for example, and in others. And from the four-dimensional side of the story, the GL formula is a corollary of certain relations, the blow-up, which are called the blow-up relations for the partition functions of supersymmetric theories in the presence of certain supersymmetric defects, which are two-dimensional defects. This was described in works by Nekrasov, for example. So for me, the interesting part is that there is this conformal blocks or Nekrasov functions, and a certain transform of them is the tau function of Painleve equation. So why is it interesting to me? Because with certain conditions on conformal dimensions of the conformal block, or from the AGT side on certain condition with certain conditions on masses of multiplets, the conformal block has a integral representation in terms of the Dyatlov-Fatayev integrals, which can be thought of as sort of matrix integrals, but in rather unusual from the point of view of matrix models theory, MIVO variables. So conformal blocks are therefore, with these certain conditions in particular, are given by some matrix models, and well, they are general. There exists even a generalization to central charge non-equal to 1. Then these matrix integrals would be promoted to beta ensembles. So from this point of view, the story from the previous page tells us that these matrix integrals should satisfy the Painleve 6 equation. And we would like to discuss how does this Painleve equation appear in the context of matrix models, and in particular for this Dyatlov-Fatayev matrix model. Also, the picture has a rather nice Q deformation on all sides of the picture. Basically, Virasoro algebra is promoted to Q Virasoro, 4-dimensional partition functions to 5-dimensional partition functions, and the Painleve 6 equation to Q Painleve 6 equation. Once again, I'm interested here in the fact that this matrix model, the Dyatlov-Fatayev representation, also persists through the Q deformation, and similar properties, statements about conformal blocks, Q conformal blocks, were made also in several papers in recent years. And so the statement is that the Q Virasoro conformal block are now tau functions of Q Painleve equations, Q Painleve 6 equation. So the objects that we're studying are the 4-dimensional. Let us start from 4 dimensions. The objects that we're studying are 4-dimensional Nekrasov functions, which are equal to conformal blocks, denoted here by ZCFT. Parameters are related in some ways, which are not particularly important for us, but just let me say that the covariant parameters on the gauge theory side are taken in a specific point where their sum is equal to 0. This corresponds to the identity central charge. Masses of multiplets are transformed into charges, which correspond to dimensions of fields in conformal field theory. And the insertion point of the operator in conformal field theory transforms into the exponentiated gauge coupling, the exponentiated complexified gauge coupling. And the letter A is also related to the conformal parameters as written, where A are the Coulomb branch parameters. So I'll be mostly speaking in terms of the conformal block. So let me specify that the conformal block depends on several parameters, which are 4 external dimensions, which are called here delta I, with the charges alpha I, an intermediate dimension delta, and it depends on the insertion point of the fourth operator, which is called here by letter Z. So the GL formula states that the tau function of the Painleve equation is given by some sort of Fourier transform in terms of the internal dimension. Here the formula is not precise. It is somewhat symbolic. More precise formulas will be, I will present them later, but basically we take our objects, either the Nekrasov function or the conformal block, and we introduce shifts of the internal dimensions. So the parameters, the tau function will depend on two parameters. Well, it will be, the tau function will satisfy a certain equation with respect to the variable z, and it will have two parameters, alpha and eta, which from the point of view of the equation are nothing but integration constants, because the equation is of second order. So what it means to be a tau function of the Painleve equation? Well, in technical terms, it means that this combination sigma made from logarithm of the tau function satisfies the presented equation, which is nothing but the Painleve 6 equation, but in a specific form, which is called the sigma form because of the letter sigma. And I will later present other forms of the Painleve 6 equations, which might be more familiar in terms of like Newtonian variables as a simple equation of second order on one variable. So as I said, if we suppose some conditions on alpha I, which will be some sort of integrality conditions, the conformal block is basically a partition function of some matrix model. Matrix models have several interesting and important properties. The first property is a set of linear equations called word identities or Virasoro constraints that the partition function satisfies. And the second important property is a set of bilinear quadratic equations which the partition function satisfies, which are related to the integrability properties of matrix models partition functions. So, of course, not every matrix model satisfies such equations, or at least not for every matrix model it's obvious how to write those equations. But as we'll see in the matrix model for the conformal block, which is, I remind, nothing but the Zankov-Fatiev integrals, these two properties will hold. However, the Virasoro constraints will be in some rather peculiar form. Also to mention, the bilinear equations are a consequence of determinant representation of the partition function. So if the partition function is given by some determinant of some matrix, then one has some linear algebra equations, or rather relations, quadratic relations between determinants and their minors. So these bilinear equations in terms of the determinant representation are nothing but simple linear algebraic relations. Usually in matrix models, Painleve equations appear in a certain pattern where we have some integrability properties described above, the Virasoro constraints, and if we combine them in proper way, we obtain Painleve equations. This is part of some general principle. I don't actually know can such statements be promoted to level of theorems, but usually if one has integrable equations, partial differential equations, one can use some constraints on the function, say look for the solution in some very specific form, and then this function, this equation reduces to some Painleve equations. And if it does, then these partial differential equations can be considered integrable. A story called the Painleve test, as I understand. However, the appearance of Painleve equations in matrix models seems to be some incarnation of this general property. On the other hand, is the phenomenon of superintegrability for matrix models. Again, the name superintegrability here is related, but rather distantly related to superintegrability in classical mechanics, say. But the general idea is that combining Virasoro constraints and integrability, which is somewhat reminiscent of combining equations of motions and again integrability, produces some exact results for correlators, averages of certain operators in these matrix models. I'm not going to talk a lot about this, but one of my motivations to study in the particular case of this conformal block and its relation to Painleve equations was to figure out whether there can be made some connections between these two properties. Does the Painleve equation somehow relate to the superintegrability property, which I will discuss a bit later. Yeah, so basically the result that I'm talking about is that, yes, indeed, the Painleve equations for the Dotsenko-Fatiev integrals, so as I said, for conformal blocks or Nekrasov functions with some particular conditions, is a corollary of integrability for these integrals and the Virasoro constraints. There are a few points to make here. First is that the picture is most clear, at least from a non-technical view. Qualitatively, it's best seen in the QD form case. And I will present it. And also, one can follow directly how this property of combination of two structures, how this property behaves with respect to taking the continuous limit or the four-dimensional limit and in the limit of pure gauge theory. Another point to make is that the technical complications which arise in this case are related to the fact that the matrix models which we are going to study and the Virasoro constraints and the integrability will be given in terms of so-called MIVA variables, which is just not really usual for matrix model theory. So the techniques are not developed enough, and therefore all calculations are rather complicated. Okay, so let me start. Yeah, so are there any questions about the motivation and basic introduction?
So in this case, I mean, the matrix model, it's a beta ensemble, but with very special beta, right? It's kind of responding to...
So I'm going to talk about only C equals 1, which is the best studied case.
Equals 1.
Which is basically beta equals 1. So it's
going
to be, oh, well.
Does it correspond to the,
well, no, depending on what you call beta, it corresponds to Hermitian matrices, basically. I will have two times beta in my van der Monde determinant, so beta will equal 1.
Yes, so it's just Hermitian ensemble.
Yeah. And whether the story promotes to general beta is unknown. Well, as I understand, it's also unknown from the point of view of the GIL formula, basically.
Yeah, at least it is promoted to C equals -2, I guess.
Yeah. It was promoted. It can be promoted to C equals -2. I guess it was done by Bernstein and Shechkin. But it's also like some point in the space of any C. So I don't know whether it can be promoted to C equals -2 in terms of the matrix model. The matrix model point of view, I will maybe touch on that later once again. But basically,
so it's beta squared 1/2, right? So it's kind of it's from matrix point of view, strange point.
Yeah, from matrix model point of view, any beta which is non-equal to 1, 2, or 4 is problematic because like the linear identities, the integrability properties which follow from the linear identities are lost.
No, basically C equals -2 is exactly beta squared equals to 2. But it doesn't matter, just go ahead.
But it would be interesting to see. I didn't really look to it yet, but yes, I know that C equals -2 case is also impossible. So maybe it somehow does promote to the level of matrix models. Okay, so let me just briefly remind some general facts about matrix models. So I will talk about mostly Hermitian matrix integrals. So partition functions are given by an integral over matrices with some measure where we will usually insert the generating function of all operators in the partition function. So the partition function will be the function of the couplings Tk. For example, the measure, for example, can be chosen as the Gaussian measure, which is the most best studied case, the Gaussian matrix model. One can integrate out the angular variables, so diagonalize all the matrices, which will lead us to simple integral over eigenvalues, which are called eigenvalue models, with the square of the Vandermonde determinant, which comes from the integration over the angular variables. One of the properties of matrix integrals, or any integrals rather, is that they do not depend on the integration variable. So one can do basically any holomorphic analytic changes of variables. Of course, one should worry about boundary conditions, and the integral doesn't change, which imposes some constraints in form of differential equations on the partition function. And this is equivalent to the fact that the integral of a full derivative vanishes again, given some correct boundary conditions. So the integrand should vanish on the boundary. So one can insert.
Yeah, may I ask you, what is mu in this equation? First letter.
Sorry, you can think of mu equals to 1. Yeah, it's not the measure. It's not related to the measure on the previous paper, on the previous page, but so it's just a consequence of me copying formulas from my paper. So mu can be equal to 1 here. So yeah, this is just an example of how Virasoro constraints can look. So in particular for the Gaussian model given here, the differential equations are presented here, and the main property is that they are linear, and one can make such statement that at least for the Gaussian matrix model, the Virasoro constraints fully determine the partition function. So one can, well, at least let me clarify a little bit. We understand this integral as follows. We choose the measure and treat all the variables tk perturbatively. So we expand. So basically, we choose some phase of this model and expand around this phase, and the expansion around this phase will satisfy such constraints. And as a formal series in the coupling variables, the partition function is fully determined by the Virasoro constraints, which is not always the case. For example, it's not the case when one promotes matrix models to non-Gaussian measures, cubic measure, for example, where choice of integration contours is involved, and there is freedom in the choice of integration contours, which is not captured by Virasoro constraints. So other property is the so-called integrability, which, as I said, is nothing but is related to determinant representations, the determinant representation of this matrix model, and means that the partition function satisfies some bilinear equations, which are usually of KP or Toda type. So fact number one is that the partition function is given by certain determinant of the moment matrix MK, and this fact alone, with certain properties with respect to differentiation, guarantees that it satisfies such bilinear equation, where the bilinear equation just turns into identities between determinants and minors.
And what is P? The derivative over P, what is P?
Derivative over P is the same as derivative over T.
T1.
Just a different notation, again, a consequence of me being not careful enough when.
Okay.
Yeah, so, and another property is the reduction of integrable equations to Painleve equations. So in matrix models, it means that the partition function satisfies some integrable hierarchy of equations, like the KP hierarchy or the Toda hierarchy. And when we impose additional constraints, like the Virasoro equations, we must obtain, we usually obtain some sort of Painleve equation. Here, there's an example which is not given by the Gaussian matrix model because it actually appears to be not the simplest example of this property, but the Kontsevich model rather. The definition is not really important, just that important is that there are those Virasoro constraints, so these linear differential equations in the T variables. And if we restrict ourselves to the sector of the first three variables, here in this equation only couplings with odd index appear, so T1, T3, T5. If we restrict ourselves to this sector, then one can write one of the Virasoro constraints in this line. Let me draw it. So this line is one of the Virasoro constraints, and where one can denote the double derivative of the logarithm of the partition function by u. And in these terms, the partition function satisfies the KdV equation. So the Kontsevich model satisfies a simpler hierarchy of equations. And combining now, if we cleverly combine these two equations, one of which is the Virasoro constraint and one of which is the KdV integrable equation, we will obtain the following equation, which is just an equation of second order in the U variable. After certain reparameterizations, this equation corresponds to the second Painleve equation. So this is an example of this property, and we are going to discuss the same phenomenon, but in a different model. But first, let me also comment on another important detail, which appears when we consider matrix models, as I said, where choice of integration contours are important. So, for example, we could consider an integral with a cubic potential, where big I denotes the imaginary unit in order to avoid confusion with the index. However, formulated in such a way, it is somewhat ambiguous because I did not specify, well, I can also specify different choices of integration contour for each eigenvalue. Such phases of matrix models are called de Graaf-Waffe phases. And well, for example, for the cubic model, we have two independent contours of integration corresponding to two minima of the potential. And the general integral is given by an integral. So the general partition function depends on two variables, n1 and n2, two numbers, n1 and n2, which denote the number of eigenvalues integrated over each contour respectively. And an important property, which is rather general, is that in such phases of matrix models, in the naive integrability, which is bilinear equations for partition functions, is lost. However, it is restored after a peculiar Fourier transform in the n1 and n2 indices. So we must consider, instead of considering a single function z and 1 and 2, in the cubic case, for example, we can consider the following sum of all possible n1 and 2, which will now restore the determinant representation with the moment matrix given by this sort of formal integral with the, well, not formal, but just by the integral with the specific combinations of contours, integration contours determined by C1 and C2. We will encounter a similar situation in the matrix model for conformal blocks in the Fadeev, in the Dotsenko-Fadeev integral.
Why don't we just set Xi2, say to 0, and why it's not in contradiction what you said in the previous slide? You said that de Graaf-Waffe. Sorry, can you scroll back to the previous slide? What you just said, that the first partition function satisfies the property of integrability, or it does not? I just missed.
Yes, you're right. There are two specific choices of phases which satisfy, do satisfy bilinear equations on their own. So when all the variables are integrated over one of the, so there are two cases, either all variables are integrated over the first contour or over the second contour. But for a general phase, it doesn't hold.
But for conformal blocks, as I remember, there's no summation over n1 and n2. It's just, I mean, the difference between them is just something like.
Well, I will proceed to this basically on.
All right.
So maybe your question will be answered. If not, I will be happy to try to answer it. Okay. And lastly, as I announced, there is the property of superintegrability of matrix models, which can be very qualitatively characterized as the following property, that the expectation value of some character is given by the character again. So I have actually already given a talk here about this property, so I will very briefly say what it means. So let us consider an example. So in the Gaussian matrix model, we can consider expectation values of Schur operators. So operators given by Schur functions of the variables, of the matrix variables. It happens so that there is an exact formula for, well, exact meaning that one can write it in some closed form, formula for this expectation value. It can be written in different forms, actually, but if one wants to generalize this as the superintegrability property, can be conveniently written as the following formula, where now we have again Schur functions, but evaluated at very special at a very special locus, where n is, well, I will not really explain the notations now, but anyhow, so we have a formula where we have some Schur operator under the integral, and the result is again some Schur functions, but evaluated at special points. This can remind some sort of localization computation or mean field computation, but no particular meaning was given to this yet. So by now it's just an observation, but an interesting observation, because this property persists along many deformations. So for example, one can make a beta consider a Gaussian beta ensemble once again, and this property will still hold. However, now one should consider Jack polynomials, which are beta deformation of Schur polynomials, so Jack polynomials instead of Schur polynomials. It also persists to Qt deformation with a, well, in the Qt case, there are some ambiguities in the definition of the matrix integral. However, still one can consider such deformations of the Gaussian matrix, Qt deformations of the Gaussian matrix models, where averages of McDonald polynomials are again given by McDonald polynomials. And in this case, the formula actually doesn't really change. So instead of Schur functions, you just write McDonald polynomials. Also, it persists to cases of, for example, matrix models with an external matrix, where we now have some external parameter parameterizing the partition function, which is also a really non-obvious case, because in the case of Schur functions, one can use well, rather simple calculation methods like Wick's theorem for the Gaussian matrix models to prove this formula. However, with an external matrix, it doesn't really. It becomes much less simpler, and it's also interesting that the functions also change. The corresponding characters are now Q-Schur functions. Also, this property persists to non-Gaussian matrix models, at least for Hermitian non-Gaussian matrix models, once again, one takes averages expectation values of sure operators. Now the right-hand side changes a bit, but is still some nice factorized formula which contains sure functions. And also, interestingly enough, it holds for logarithmic models. So if we consider such integral, even beta deformed, excuse me, there are two van der Monde determinants here. This is a misprint. So we consider beta deformed eigenvalue integral. So with a logarithmic potential, which reduces to such an integral, which is already reminiscent of Dotsenko-Fateyev integrals. And even in such models, there are such formulas in superintegrability formulas. So for example, for the expectation value of Jack polynomials, it will be given in terms of Jack polynomials once again, but in a highly non-trivial fashion. As a result of work of various people, including myself, in latest years, it now seems so that the superintegrability property is a combination of Virasoro constraints and determinant representations, or which means integrability equations, it becomes more clear and clear that that is the case. So, for example, what one does is one uses the determinant representation to write an expectation value of sure functions as determinants of the moment matrix. And then the Virasoro constraints, which are usually differential equations, turn into simple algebraic equations, which is again sort of reminiscent of the picture in classical mechanics, where superintegrability means that, well, at least to some extent, it means that all our equations of motions reduce to some algebraic equations. So here it reduces to some algebraic relations between these sure averages, which can be explicitly solved and give the formulas that I have just shown on the previous page. So the general idea is that, as I said, there are two ways. It seems like there are two ways to combine Virasoro constraints and integrability equations in matrix models. One way produces somehow Painleve equations, another way produces explicit formulas for averages. And of course, an interesting question which motivates this work in part is to find some relation between these two properties. Okay, so let me now proceed to describe the type of matrix models which we are going to consider for the relation with the conformal blocks and the Painleve equation. So let us consider an Hermitian matrix integral, but now we will change the variables as follows. We will say that the variables tk expand with the ZA variables with some multiplicities alpha A, which basically means that we make the following change of variables: tk equals 1 over k, trace of some external matrix m to the k, and now so the z variables are eigenvalues of this matrix, and the alpha variables are nothing but multiplicities of these eigenvalues. So in terms of these variables, one can rewrite the matrix model, and it will look as the following integral, which is of course equivalent to taking the logarithmic potential of inserting a logarithmic potential inside the matrix models, inside the matrix integral. So therefore, I will sometimes call these models logarithmic. And As I said, this is reminiscent. The simplest case is when only two multiplicities are non-zero, and we return to the already described model, which actually has this beautiful superintegrability property. So the conformal block corresponds to a phase of this integral of this matrix model where we have three non-zero multiplicities, alpha 1, alpha 2, and alpha 3. In this case, we already have two independent choices of integration contours, which of course correspond to the two contours of integration for the conformal block, C1 from 0 to Z and C2 from 1 to infinity, where the multiplicities are related to conformal dimensions as before. And here we see that in order for this to represent the conformal block, there have to be relations between the charges. So basically here the conformal block actually depends on 4 charges, alpha 1, alpha 2, and alpha 3, and alpha 4, and their sum should be related to the dimension of the matrix model. So in order for this to be a properly defined matrix integral, n should be integer, or rather positive integer. So that means that not all cases for conformal blocks can be described in that way. However, one may argue, if one wishes, one may argue that answers have proper analytic continuation in terms of n, but then one should worry about presenting the answers in such form that they will have a proper analytic continuation. This is not what I will be interested in. However, that's an important moment, and that's an important point to be made. And once again, the conformal block actually depends on another parameter, which is the dimension of the internal operator in the conformal block, which runs in the conformal block, which is denoted here by alpha. And in fact, the proper representation of a conformal block with dimensions given by delta I and delta is by the graph of alpha phase of such matrix model in terms of n1 and n2, where this letter here is some prefactor given by Barnes functions, which are of course important for calculations, but will not be important for my qualitative discussions. So we are forced, well, at least if we want to motivate ourselves by conformal blocks, we are forced to study the graph of alpha phases of such integral. And of course, so it's given precisely by the following integral. We have two integration contours, n1 plus n2 variables. And once again, the determinant representation. So we expect this model to have a determinant representation. However, it is broken after we consider generic n1 and 2. But as I said, the general theory dictates that in order to restore the determinant representation, we should make this Fourier transform in n1 and 2. This can be done, and the integral does have a determinant representation in this case. So this particular Fourier transform appears to be nothing else than the same Fourier transform of the conformal block, which is usually considered, well, or was considered in the original papers by Gamagin, Yorgov, and Lissavi. Here, one can see that the sum here goes over this letter K, which is the difference between N1 and N2. And as we have seen on the previous page, the difference between N1 and N2 is nothing but the internal dimension alpha. So the sum is actually over shifts of the internal dimension, just as it should be in the GL formula. But in this case, due to this integrality conditions, the sum is actually restricted to very specific interval between k equals 0 and k equals n.
I think psi 2 should be to the power n1 plus n2, I guess. Otherwise, in front of the sum, right?
Let's see.
Otherwise, it doesn't reduce the difference.
Oh, it should be to the power n2. Sorry.
No, I guess n1 plus n2.
Yeah. Wait, sorry. Sorry, it's let me see.
So it's proportional just to the sum of charge. So it's just n. Yeah, without index, just n.
Yeah, just n here.
Mm-hmm.
Yeah, not in one. Okay, so the conformal, so the Fourier so just as in the original construction, the Fourier transform of the conformal block is some nice tau function. Here we see that this Fourier transform is needed to restore the integrability properties from the point of view of matrix models.
So may I ask also, but here the sum is finite, right?
The sum here, this sum.
This sum is finite. I mean,
it's restricted to this interval, which is a result of these conditions. Certain sums of charges are integers.
Yeah, I mean, compared to this key formula, it's
yes, but compared to this formula, but if you consider the same formula and insert and put the condition of relations between charges, you will again obtain finite sums. They will reduce the sum of these intervals.
It becomes a finite sum for this. I see. So,
so one should impose these conditions, and the sums become finite.
Oh, I see.
So so now, as we have restored the integrability properties, let us see what they look like. In these MIVA variables, the Hirota equations for the KP and the hierarchy are difference equations in these multiplicity parameters, alpha. So here there are various forms to write them, and so here are just some examples. You take partition functions specified by n and parameters alpha. You make shifts by 1/2 of the parameters, and it is bilinear in the combination zn minus 1. So in this form that is written here, you have related are partition functions with also shifted parameter n, which actually corresponds to shifts in the parameter in the multiplicity in the charge alpha 4, because here alpha 4 is hidden in the number of integration variables n. So this is quite well known. This is just standard knowledge. What is more peculiar are the word identities or Virasoro constraints in terms of these MIVA variables. So let us start with a simple case where only two multiplicities are non-zero. So this is some generalization of the beta function. I call it beta n, some sort of multiple beta function. So how to construct some sort of Virasoro constraints for this model. So the naive way is to insert full derivatives. So here I just give an example for n equals 1 when there's no van der Monde determinant. So we insert a full derivative here because of the structure of the integrand. It vanishes on the boundaries, at least for positive values of alpha. And in this way, we derive this relation equation for the function beta1. At the same time, one can consider the Hirota equations to see the difference between the two. So, in fact, if one writes Hirota equations for this simple function beta1, Hirota equations of such form, here there will be no term with shifted n because n is already equal to 1 and z of 0 is just 1. So these relations also become linear, but we can see the difference. In fact, the Hirota equations are nothing but identities which we insert under the integral. So they do not depend on the existence of the integral. More let's say conceptually, it means that Hirota equations do not depend on the measure, really. So we could insert here any deformation. So instead of dx, we could insert any deformation of the measure, and still the Hirota equations will be present. I forgot to mention this in the very beginning, but this is a general property. In all the previous formulas, let me spin back a little bit. In all the previous formulas, the determinant representations and the Hirota equations were written for partition functions with an arbitrary measure. So, as I said, this needs a little clarification, because depending on the measure, one can have multiple integration contours. But if we don't deform the measure in this dramatic ways, we can insert, say, powers of x here, then the integration contour doesn't change. So then the partition functions will still be partition function of the matrix model will still be a tau function of the integrable hierarchy. So here we see a particular realization of this case. While Virasoro constraints do depend on the measure, the Hirota equations do not. So if we would start from this beta function with an arbitrary measure here, we could still write the Hirota equation, but then we will have an ambiguity in choosing the measure. And this ambiguity is actually fixed by this Virasoro constraint. So this Virasoro constraint specifically tells us that the measure is not arbitrary, but is given by this beta type integral. So, of course, this property persists to the case of many variables. However, now it becomes a little more peculiar than usual. So here comes the technical difficulty. However, well, maybe it has some, well, it should have some conceptual meaning, which is not clear yet. But the technical idea is that now Virasoro constraints are also written in bilinear form. So what we like to do is we like to write this Virasoro constraints as some operator, differential or difference operator that acts on the partition function, like in this case, right? But it appears so that when we consider many variables, it is not possible to do. Rather, it's given by some it's given by some expectation value in this for this measure, but is not written in terms of the partition function itself. However, this property can be restored if one multiplies this result by, well, in this case, beta1, and reshuffles the variables, which allows to obtain the following equation, which is now bilinear. So this is a simple example of this of the general property that such matrix models, such models parameterized by MIVA variables have. So for comparison, once again, I list the Hirota equation. One can see that the characteristic property is that the coefficients here depend on the multiplicities, but here they do not. So once again, it means that we can freely change the measure here by just changing the multiplicities in the Hirota equation, but we cannot do it here. So aside from the technicalities, the point that I'm trying to make is that here, in this case, Virasoro constraints, or the analog of Virasoro constraints is also bilinear, which we'll encounter later, and this will be an important point. So, yeah, if there are no questions, I want to proceed to talk about the Q deformation. I won't go into any details. Actually, on the level of matrix integrals, the Q deformation is rather, well, I wouldn't say trivial, but it's rather straightforward. So if we talk about Q-Virasoro conformal blocks, we need to study the Q-Virasoro algebra, or in terms of Nekrasov functions, we need to study 5D gauge theory, but in terms of matrix integrals, the generalization of Dasenko-Fateyev integrals are just given by substituting usual integration by Jackson integration, which is defined here. So this dqx of function x is given by the following series, and the substitution of these like differences by just Pagamer symbols. So the deformation of the matrix integral, now the Q deformed integral, is just the same integration, but with the Jackson integrals instead, and the Pagamer symbols instead of these differences. And the Virasoro constraints can be derived, well, conceptually in a similar manner, of course, technically a little bit more complicated, because of the property that, again, given appropriate boundary conditions, Q integral of a Q derivative also vanishes. So where the Q derivative is the following difference derivative. So now, so yeah, for example, again, for this beta n function, the Virasoro constraints would look like this. So actually everything that happened is that constants, well, coefficients to alpha were promoted to Q numbers. But an important conceptual point that happens is that if one looks at, let me see. Yeah, so the Q Virasoro conformal block is then defined as follows. Once again, one should integrate n1 variables against one contour and 2a variables against the other contour. And well, after every rescalings and everything, one obtains the following Q integral, which again can be restored to an integrable form, well, to a form which satisfies bilinear equations, let's say, by this Fourier transform. So yeah, let me.
Yeah, but somehow the symmetry. I mean, the integrand is not symmetric. I mean, n1 and 2 equal. They enter differently, right? So,
well,
I'm looking at the last term, 1 minus z uivj squared. So it's kind of, so the Q deformation.
This appears after certain reparameterizations, because actually, well, it's not written explicitly here, but what I did here was take integrals over, for example, this contour, rescale variables in such way that it would be an integral over this contour. I did was take this contour and again rescale, make conformal transformations so that it looks as an integral over this contour. And this made the
Yeah, I see.
asymmetric.
Mhm.
So an important point which I didn't include is that now if we write the Virasoro constraints, well, just as for the beta function, for the n multi-beta function in the QD case for the functions for the conformal blocks for integrals with 3 non-zero multiplicities, right? What will happen is that they will be difference equations not only in the alpha variables. So in terms of alpha variables, we'll still have shifts of this type in the equations. They will be also difference equations in terms of z, in terms of z variables. What we will have to do is promote combinations like fn, say, of alpha plus 1/2 z fn minus 1 alpha minus 1/2 z. We will have to promote them to, of course, now, so 5-dimensional, but we'll have to include q here and q minus 1 here. So what will happen is these variables become the alpha variables, which actually now enter in combinations q to the power of well, some alpha, and the z variables now become more symmetric, so they're treated on equal footing. The equations are now different in both types of variables, which is actually a manifestation of some deeper properties. Well, for example, for the Q hypergeometric functions, there are relations that mix up the coefficient and the variable. Well, with the parameters and the variable. So this will be technical reason for the fact that in the QD case, the equations look, the structures are clearer. Okay, so I have basically finished reviewing properties of matrix models in MIVA variables. So I have described the types of models we're looking at, which on one hand describe conformal blocks, and on the other hand are supposed to satisfy some Painleve equations. So let me now briefly introduce the Painleve equations. So I'll start with the QD case. In the QD case, the sixth Painleve equation. So it should be rather titled not just Q Painleve, but Q Painleve 6. So the sixth Painleve equation is given in the form of pair of difference equations on two functions, W1 and W2, and with certain parameters A and B, which in terms of our matrix model parameterization are given by the following combinations of the alpha parameters and n, now all exponentiated with respect to q. So this is so this system is called the Q Painleve equation. I will not. Well, I don't have time, and I will not go into details describing properties of these equations. Instead, let me proceed to give the following form of the Painleve equations, which I'll be interested in. So, well, one can argue that one particular parameterization for the Painleve equations is given by the following set of 8 difference equations on 8 tau functions from tau 1 to tau 8, So this is again kind of standard in Painleve theory. Well, it comes. It can be described either in terms of, I suppose these are called mutations, or in terms of this property of confinement of singularities of the Painleve equation. So it can be argued that one can parameterize the whole system in the following way. So this notation tau bar is just tau of qz, and tau under brace is tau of q minus 1z. So this is nothing but a system of difference equations on some set of functions. And if these difference equations are satisfied by functions tau, then the following combinations W1 and W2 are solutions of the Painleve system of equations. So these equations are interesting to me from the matrix model point of view. Once again, in order to make the connection, one has to notice that in fact these equations can be written in terms of one function with shifted parameters. So all these tau functions, tau1, tau8, are actually parameterized by 4 letters, alpha 1, alpha 2, 3, and 4, which are of course related to, well, for general Painleve theory, these are just parameters, but of course they are related to the multiplicities or dimensions or charges in the conformal blocks. So after such parameterization, the equations here are transformed into nothing but difference equations in tau, in alpha and z. So one can see that all the equations are written for functions of this type. So tau bar tau for combinations of this type tau bar tau. So they are difference in the variable z. And because of this parameterization, they are difference equations in the alpha variables. And so the theorem is that if the function tau satisfies this difference system of equations, then this ratios of these tau functions satisfy the Painleve system. So we are interested in looking at these 8 equations from the matrix model point of view. So it appears, to make the connection, we basically state the result. So this is the result that the conformal block. So it's known that Q Virasoro conformal blocks solve our tau functions or Painleve equations. So in this case, one doesn't need to introduce the sigma form, just simply the conformal block itself is exactly the tau function. So of course, as we are discussing some particular case, so some of conformal blocks with some particular conditional multiplicities, our partition function is also tau function of the Painleve equations. So it's simple, please to check that such defined in such a way partition function satisfies the following set of equations. So one can simply check this. So of course we argue that the matrix model partition function also solves the Painleve equation, the Q-deformed matrix model partition function. So from the matrix model point of view, these 8 equations actually have a distinguished property. Mainly is that from the matrix model point of view, they have a very transparent origin. So 4 of these equations are analogs of Hirota equations, and the other 4 of these equations are analogs of Virasoro constraints. So as I discussed, so my whole discussion about Virasoro constraints in pre-deformed models was to make the point that both the Hirota equations and the Virasoro constraints are some bilinear difference equations on the partition function. And it appears that these 8 equations are nothing but sets of such bilinear difference equations. So at least on the level of checking the formulas, one can do the following thing. One can try to change the measure in these integrals. So insert some, let's say, z to some power, u to some power in here, or maybe sine of u. So make an arbitrary change of measure under the integral, and find that the first 4 equations actually still hold for this partition function. So the first 4 equations do not depend on the measure, and this is a characteristic property of Hirota equations. So one can show, I will demonstrate it on a simple case, that these relations are nothing but determinant identities between the partition functions. So one can actually see it in even simpler. In order to see it, one have to notice that so what one does is one can write the Pagamer symbol as the following product. So let me not make a mistake. So each Pagamer symbol is the following product, and in fact, it is nothing but just an incarnation of the general integral. So here, the general Hermitian integral in Miva variables is such an integral with many non-zero multiplicities. So expanding each Pagamer symbol, we in fact see that this is the same integral. And the interesting property is that since the Hirota equations do not depend on the contour of integration, on the measure of integration, they also don't depend on the fact that we have Jackson integrals instead of usual integrals. Well, because Jackson integrals can be thought of some integrals over, well, with a very specific measure and encircling some particular poles of this specific measure in order to reproduce such an expansion, right? So it's very easy to see that the first 8 equations are in fact just Hirota equations for our partition functions, for the matrix model partition functions, and the other 4 equations can be seen to depend on the measure. And this is a particular characteristic property of Virasoro constraints. And one can try to identify them as certain insertions of a full derivative under our initial integral. So let me give you a simple example here of how everything works. So again, in the example of n equals 1, everything is linear. And out of these 8 equations, only 2 are independent. So, and one of these equations does not depend on the measure, and the other does. So these 2 equations are one of the 4 in each case. So in terms of the partition function, these equations look like this. They are rather similar. So here I only I've only spelled out the indices that are shifted, so all the others are not shifted. But even though they look similar, they in fact have a different nature. One can be written as a simple identity under the integral. So this formula equals 0 without taking any expectation value, so without any integration. However, the second equation is nothing but an insertion of the full derivative for such an integral. So as we see, indeed, so the equations that do not depend on the measure are related to the first four equations and related to integrability and determinant representations of the matrix model partition function, while the second equation is related to Virasoro constraints. For general n, all of the four equations are nothing but the Virasoro constraints. So the main statement in the Q-deformed case is that one has these 8 equations which are known to give solutions to Painleve equations, and it is known, so it has been shown that Q-Virasoro conformal blocks satisfy these bilinear equations. From the matrix model point of view, it means that the Q-Painleve equation is a consequence of taking together the integrability equations and the Virasoro constraints, just as I announced in the beginning. So, and as I showed in examples, what one does in the Kontsevich model to reproduce the Painleve equation, one restricts so we restrict ourselves to a certain number of variables and combine integrable equations with the Virasoro constraints. This is just what happens here. So we take the general matrix integral, restrict ourselves to only 3 non-zero multiplicities, and write down the bilinear relations which are Hirota equations, and also write down the Virasoro constraints which appear to be also bilinear in this parameterization, so for these models. So which is a rather peculiar property. Usually one says that word identities are linear equations for the partition functions. So we see that the statement which I trying to announce is indeed true in this case. And next, I would like to demonstrate that, in fact, this property holds and persists in the continuum limit. So in the continuum limit,
so yeah, may I just clarify the form? I mean, the exact form. How to say? The exact form of which expressions you substitute on the integral is written in your paper. I mean, for general case.
Yeah. So this is a important question. So to clarify, we weren't able to identify the general form of the insertion.
Mm-hmm.
It's possible to identify in each case for each n. However, the expressions lack some nice structure, so we weren't able to derive the structure. So what we can't do is demonstrate explicitly which insertions of full Q derivative we need to put. However, what one can do is to demonstrate that these equations do depend on changing the measure. So in fact, do
not depend or depend.
They do depend. The one that we consider Virasoro constraints, they do depend on the measure, and well, therefore there really cannot be anything apart from Virasoro constraints, because when you have an integral, there isn't anything more than identities which hold under the integral, and the fact that the integral is of a full derivative vanishes.
Mm-hmm. Mm-hmm. Thank you. So,
okay, so let me proceed to the continuum limit. In the continuum limit, we expect to see solutions to the usual differential Painleve 6 equation. Once again, very mistakenly forget everywhere to write that this is the Painleve 6 equation, because there are actually, well, there's a hierarchy of Painleve equations from 1 to 6. So this is the sort of highest equation in the hierarchy. And in terms of, so I have already written out this so-called sigma form of the equation in the very beginning. Here, so here I don't know, you can call it the usual form. I call it the Newtonian form of the equation because it looks like a Newton equation of second order. So here's this form of this equation, so the general knowledge is that as I said, is that the usual conformal block for C equals 1 is the tau function of the usual Painleve 6 equation. So, and I remind that usually it's written in the sigma form. So one takes the sigma, writes as z minus 1 d log of say the conformal block, d log over dz, and this would be the so this will be a solution of the sigma form Painleve equation. However, so it is really simple to notice that from the Painleve equation, after taking the continuous limit, one in fact obtains the other variables. So the dynamic variable W1 has a simple limit. So it has a simple continuum limit. So we just simply take the limit q to 1 in the expression and obtain the ratio of these tau functions, which are just limits of the tau functions for the Painleve equations. So limits q to 1. So for the second variable, the limit is more complicated and involved. The second variable W2 relates to the so in fact the form of the Painleve equation is such that they are first order difference equations in two variables, and they in fact reduce to a Hamiltonian form of the Painleve equation. So and then this is the coordinate variable W1, and W2 is related to the momentum variable, but in a more complicated way. So here for me it's important just that what we obtain after the continuum limit is the function W of z. So and the parameterization. So if we did take the continuum limit correctly, then the limit of q to 1 of these tau functions, this ratio should solve the Painleve equation in the second order form. And indeed, this is true. So, well, at least one can check this is true. I will argue that, that this is true. So, apart from the, I would say, standard, I don't know, usual representation of the solution of Painleve 6 in terms of conformal blocks, which is in terms of sigma form, there is actually a second form in terms of the ratio of conformal block scopes. I'm sorry, there are this q here, which are so one should of course take the limit q to 1 here. So the ratio for just usual conformal blocks or for Dini-Krasov functions with shifted parameters solves the Newtonian form of the Painleve 6 equation. I don't actually know if this is a known fact. Maybe it's not. Maybe it's not important. I don't know. So, but at least if one considers this continuum limit, there is this. Well, there isn't really nothing to know here because it's rather trivial. But I didn't really see people writing it in this form, and I don't know whether there is a reason for this. so yeah, and the connection between the two is actually rather interesting because it appears that there is this rather complicated formula that connects two forms of the Painleve equation. So from W it makes this from the Newtonian variable it makes the sigma form variable, and in fact to relate these two one should also consider this sigma form not with the usual parameters but with shifted parameters. So if here the Newtonian variable is given by the original conformal block with not shifted parameters. So in order to relate it to the usual sigma form, one should take the partition function or the conformal block. I don't actually know if this actually can be lifted to the level of conformal blocks without this constraint. Well, at least, so what I know is that this holds for the matrix model partition function, but you should shift the variables, and looking carefully, one can see that this shift of variables is just a background transformation for this Painleve 6 equation. So this is just a bunch of, I don't know, funny facts. I don't know if they are important, but they are at least side products of the calculation.
Yeah, just sorry, I missed a bit, but in the original GIL formula, you would expect to have Z with, I mean, this with your standard kinematics, right? So alpha 1, alpha 2.
No, you can, yeah, of course, you can do it in that way, but then in this, you can take the original, as in the original formula, you can take the set of alpha 1, alpha 2, alpha 3, so n. So this fixes alpha 4, right? But then for this W variable, you will have to take some really weird, well, also just as weird as this. So Backlund transformed the parameters in this W variable.
Well, this is true. What you're just saying, I mean, you can do other way around. You can start.
Yeah, you can do other way around. This is I just listed in this way. Well, so here in my parameterization, one has the original parameters alpha 1, 2, 3, 4. Yeah. Then for the usual parameterization, you will have the shifted parameters. So you can do it other way around. Put here the original parameters alpha 1, 2, 3, 4, and here have the shifted parameters. Yeah. These theta parameters are nothing but alpha parameters. Like 0 is I recall alpha 1 and so on.
Yeah. I was trying to ask the sum of alpha, this effective alphas is also in integer.
Yes. Here, so one should understand. So one here should understand the alpha 4 multiplicity. Let's say as so. Let's see. Sum of alpha I is minus n. For 4 is basically minus sum of alpha I from 1 to 3. So instead of alpha 4, here we have this n.
And this transformation, this Backlund transformation, it does not somehow it doesn't change alpha, the intermediate alpha. It doesn't change it. It does. It just.
So no. What you do is take all your alpha i's. So this Backlund. So there are several Backlund transformations here. I didn't write it out because I didn't want to waste too much time on it. But what you do is you take alpha I into alpha I plus or minus, I don't remember, half sum of all alpha.
Yeah. But that's what.
Yeah. So basically, what you do is because half sum of all alpha I is n over 2. That variables are shifted with respect to n over 2.
Got it.
There are some shifts with the one half shifts of variables.
I see.
Yeah, so basically the statement is that so the usual JL formula gives solution of Painleve equation in the sigma form, but well, you could expect that the solution in the Newtonian form is rather ugly, but it appears to be also rather pretty. Well, I don't know what else to say about here, but maybe it's some interesting fact. So, but what is important to me is that I want to show that the structure behind the relation of integrable and Virasoro equations and their relation to Painleve equation holds in this case too. So in fact, one can write a system of 8 equations of 8. Now they are going to be differential equations on this tau functions, now undeformed tau functions. So here are only 6 equations. The other, or rather, yeah, 6 equations. The other 2 are on the other page. So, these equations are going to be continuous limits of the original 8 equations for the Painleve system. So basically, the claim is that now they are different and differential. So difference in terms of alpha parameters, differential in terms of the z parameter. Here, d log z is the logarithmic Hirota derivative. So now z and alpha are on different footing. It makes the equations a little bit more ugly. But anyhow, so here, for example, psi ig is some quadratic polynomial in alpha and n and z, which are just a little bit too long to write them on one page. So what is important is that, again, we have 8 equations for our tau function, for our partition function, matrix model partition function. And closely examining them, we can see that, again, 4 of these equations actually correspond to Hirota equations, and the other 4 are again measure dependent and hence correspond to Virasoro constraints. So the ones that correspond to Hirota equations are quite simple, could be written down easily. So one can again argue the same logic that one can change the measure and so on, so on. So the structure of the relation between integrability and Virasoro constraints and their combination into Painleve equations persists in this continuum limit. Yeah. So, and the statement is that, of course, is that these 8 equations, from these 8 equations, one can derive the Painleve equation for the combination tau 1, tau 2 over tau 3, tau 4. So, of course, this is a rather messy calculation, but from this list of equations, one can derive the Painleve equation. So once again, from Virasoro constraints and integrability, one derives Painleve equations. Yeah. So as this, so as I say here, so the structure persists. Virasoro plus integrability is Painleve equations. Yeah. And so lastly, let me briefly discuss the so-called pure gauge limit. I'm not going to talk too much about it, so I'm not going to spend much time explaining notations. But basically, it corresponds to, in the gauge theory, it corresponds to sending all the masses to 0, while holding a particular combination finite, because after we take the pure gauge limit, the theory stops being conformal, and one has the sort of QCD scale as another parameter. So one should fix the QCD scale as finite. So in terms of the Painleve equations, it means that one takes the z variable and rescales it with the alpha variables, takes alpha to 0, then what happens is that the tau functions and the w functions solve not the Painleve 6 equation, but the Painleve 3 equation, which is also well known. But again, so what's interesting from the point of view of matrix models is that, again, one can see the structure of two properties combining into Painleve equations. So basically now, so this limit is not really well developed in terms of the matrix model. So the Zankov-Ateyev integrals are so it's not clear how to go from the Zankov-Ateyev integrals to this Brezin-Gross-Witten matrix model. However, so the statement is that one has this matrix integral over unitary matrices, which is the standard Brezin-Gross-Witten model, and so the pure gauge limit partition function is formulated in terms of two pairs of such integrals. So one takes two partition functions and integrates them with certain weight. So these functions Z1, and one takes, once again, the Fourier transform of this function Z in terms of some variable A, which is, of course, the remnant of multiplicities, or in terms of gauge theories, the remnant of Coulomb branch parameter. So once again, one takes this Fourier transform, and this Fourier transform satisfies the Painleve 3 equation. So what one has is this function, and one can show that it has two properties. One is that it satisfies the Toda equations. Here, this is nothing but the bilinear form of the Toda equations, and it also satisfies a certain reduction. So this shift of the A variable with respect, so A plus 1 equals this Z of A, and taking these two conditions into account, we reduce the Toda equation to the Painleve 3 equation. So this is just the tau function form of the Painleve 3 equation. Here is the square is missed. So this is a quadratic version of the Painleve 3 equation. So this is just to demonstrate that this structure persists in different limits, and so always in terms of the matrix model, one has the same argument that one has two structures, integrability and Virasoro constraints, or some reduction constraint. Well, one can actually see that this reduction constraint follows also from Virasoro type equation. So, and these two structures combine into Painleve equations. So when one considers conformal blocks, one recovers the GIL construction that the Fourier transform of the conformal block, now in terms of the Zankov-Ateyev integrals, satisfies the Painleve equation, and also, of course, one recovers for the Q-deformed matrix model, one recovers the Q-deformed version of this formula. So the partition function satisfies the Q-Painleve equation, is a tau function of the Q-Painleve equation. Yeah, so that's basically that. So in C, so we know that C equals 1. So we know two things: C equals 1 conformal blocks and their corresponding dual to the Nekrasov functions satisfy the Painleve 6 equations, and we know that from several points of view. Let's say from the four-dimensional point of view, it corresponds to defect partition functions, properties of defect partition functions. from the conformal point of view, one can argue from properties of Virasoro algebra and from monodromy properties of the conformal block. At the same time, we know at the level of matrix models the statement that Virasoro constraints and integrability combines into Painleve equations. And since conformal blocks at with certain conditions on charges are described in terms of some matrix model, we of course expect the same. So expect the Painleve equation to be a manifestation of this structure in matrix models for the cases when they are described as matrix models. And we find that this is indeed the case in Q-deformed case, in the continuous undeformed case, and in the pure gauge limit, in which case it's even simpler. And as I mentioned, the interesting mystery here is that there's this beautiful superintegrability property. Of course, the first mystery is whether this property is actually something meaningful. But if we hope that this property is meaningful, then we can ask whether it's somehow connected to Painleve equations, because both are a result of combining integrability with Virasoro constraints in matrix models. Okay, so that's pretty much it. Thank you for your attention. Thank you for inviting me.
Thank you. Your questions, please. Yeah, just I want to make sure. So in for D limit, I mean those insertions in the integrand you found in 5D case, do they have the smooth limit? So I mean, do you understand how to derive those, at least in particular cases, how to derive the word identities and Hirota equations?
Yes, of course. So, for example, well,
yeah,
at this very simple case at n equals 1, so this is an insertion of a Q derivative. One can rearrange terms such way that it corresponds to an insertion of the usual derivative in the usual integral of just the 3-point integrand, 4-point integrand.
This is just one of 8. This is just 2 of 8 equations, right?
Yeah, in case n equals 1, all the 8 equations they so they reduce to only 2 independent equations. But in other cases, yes. So just for specific cases, one can find the insertion and then one can follow them.
But from general like settings, do we expect some? If this insertion, for example, the degree of the polynomial which insert can be predicted, it is fixed or not?
Well, one can predict. Well, so this is not really clear enough. But well, what one can do is, for example, here. So the simple demonstration of this effect is that when you have shift in parameters, this shifts in parameters correspond to the degree of the inserted polynomial. So that way, one can of course look at the equations. If we start with equations and try to derive the insertions, then one can look at the degree of the shift and try to look for insertions in such way. But the main complication comes from the fact that there are many variables. So there are many sort of ways to make these insertions.
Yeah, but is it true? Like, suppose I have found all those eight the symmetries, 8 kind of generators. Do they generate the wall? I mean, the wall set of identities somehow.
So the basic idea here, there are 2 basic ideas here. So the first is that for example, for the usual Virasoro constraints in the matrix model, so one actually needs only two constraints, L-1 and L2, right, to derive the whole. So since it is the upper part of the Virasoro algebra, one needs only two of these constraints. On the other hand, so at least phenomenologically, I would say so. So since we know that combining this linear equations, or rather the determinant form, with the Virasoro constraints has to completely fix the partition function, well, at least in cases where there are no ambiguities of contours. It means that cleverly combining only single Virasoro constraint will already, with integrability, will already derive all other Virasoro constraints. Just like I tried to demonstrate here. So if we use this determinant form only from the L-1 constraint, we can find all the averages of all Schur operators. Therefore, we can reconstruct the partition function. Therefore, we can reconstruct all Virasoro constraints. However, how to do it technically, this is of course a different question.
Okay, so maybe somebody else has a question. Oh, okay, so then thank you. I think the official part is over. Да, Вики, я хотел, можем как-нибудь встретиться, поговорить, просто я сейчас, ну, не буквально я, но я, вот, так сказать, стал думать, тоже надо над похожей задачей. Я просто что-то забыл, что так тоже можно это изучать, вот, делать, ну, доцент Хватеева. Вот, не знаю, у вас как вообще со временем?
Ну, в зависимости от того, где...
Где-то в Москве.
Вот можно в МГУ, в ТМФ.
Ага.
Я там бываю по вторникам и в среду утром, например.
В среду утром. Угу.
Ну, вторник я там типа целый день почти. Ну, там до вечера, до где-то 6.
Кстати, а вот если я подставлю условия скринирования, когда бета произвольная, там тоже только конечное число членов останется? Сумма тоже конечная будет?
Я не знаю, в смысле, ну, а вот разве когда бета произвольная известно, ну, чтобы это была вот эта вот формула и так далее, чтобы это все имело смысл?
Нет, ну я просто... ну, видимо, сейчас... Не, ну если эти blow-up-формулы, они бесконечная сумма, да? Ну да.
Ну, то есть, сейчас, ну, как бы, если просто вот говорить о том, что так, если